What's going on, everybody? It's Mr. Gustin. I'm back in the physics classroom, and today we're discussing an idea that generally trips students up. And the idea is the difference between an object that is which finger? A point mass and an object that is a sphere. And a sphere you can replace with any rotating object. But for the first part of this unit, we mostly study how objects roll, how their angular momentum and energy is dictated by their shape and their size. They roll down inclines, they roll into things, they roll up inclines, they launch off tables, they roll down ramps. This is how we study physics initially. And as we get into angular momentum and angular collisions, what we start to see is objects that are spheres, like this tennis ball on a string here, they now start to roll, but they start to move linearly in collisions and cause rotation. We can think our ballistic pendulum. We can think our marble down a ramp onto a magnet. And so things start to get tricky where the angular momentum the angular momentum is not around the axis of rotation of the marble, or at least the angular momentum we're concerned with is not around the marble, and it's relative to a different axis point. So I have to go back and think about what our equations mean, what variables mean, and how we're explaining physics about point masses and then also about spheres. I'm trying to get this mirror image thing down on the video. So we're going to do that today. Let's go back to our original physics where we have objects like this tennis ball, like a sphere. A sphere, and as a sphere rolls across a table, if we're thinking about the angular momentum, rotational inertia of this sphere, we are thinking about it relative to its axis of rotation. And as it rolls, the axis of rotation is right in the middle of the object. So any kind of momentum this object has about its own axis of rotation stored within itself is about that axis of rotation. Now, we can also think about this a very different way. Perhaps this object is not rotating around itself. Perhaps this object is rotating around a fixed point, like say this, my finger. If I go ahead and put this string around my finger, well, now this tennis ball is going to rotate around this axis of rotation over here. And if this is the case, its angular momentum is much different than, say, if it's rolling, now it's about this string. So as I go ahead and yippee-ki-yay this thing around, in a circle, don't hit the board, Gustin, like this, its radius is now from the mass to my finger. So those are two very different radii, and when I have two different radii, I have two different rotational motions. I have a sphere, and when I'm thinking about a sphere's motion, if I'm concerned about the sphere's angular momentum, the axis of rotation is here, and I'm thinking about this radius. That's what this is. It's rotating around itself. I can use 2/5 mr squared. If I'm thinking about what a point mass is a mass that we simplified to a single point. And it's a single point that exists at a distance, let's call that distance r, away from the axis of rotation. This point mass travels in a circular path around about that axis of rotation at that radius. And the reason it's mr squared is because if I were to take this thing spinning over my head and speed this video up 1,000,000 times, what you would see is that this point mass creates a very, very, very thin hoop. And so this I value is essentially that for a thin hoop. It is mr squared. And so when I think about various examples of conservation of angular momentum, I think about an object. For example, we used a launcher that launched a marble out with an initial velocity at a hanging magnet or a hanging mass. When I think about this idea, when this marble does eventually collide with the magnet, here's the axis of rotation. It swings itself in this direction. So ask yourself, is that a point mass or is that a sphere rotating around itself? Where is this object moving about? My physics is relative to what axis of rotation? And when I'm thinking about this motion, I am thinking about how this object moves closer and closer and closer to this magnet. I'm thinking about this motion relative to this axis of rotation means this object here is a point mass. In a different scenario, if I'm thinking differently about something, a different kind of collision might be something like a turntable and a barbell dropped, or a barbell weight dropped onto it. This is our first example of a sphere being a point mass. Let's think about a disk. What if I have, like we did in class, an example where I have a rotating disk? And I could draw this from the side and be like, here's my rotating disk. It's rotating around this right here. It's rotating like this. And then I have another smaller disk of mass waiting above it. I drop that disk. This is its initial angular speed. After I make that drop, now I have this disk and this disk sitting on top of it. It moves much slower. This is its final momentum. If I'm thinking about this, right, the disk itself is rotating, bird's eye view. The disk itself is rotating around this axis of rotation. This is the radius I'm going to use. I would call this object here, this is a disk. Because the physics that we are using, the way we are examining this scenario, is about that axis of rotation. It's another example of how, based on the way we define our system, based on the way we study the system and the scenario we're looking at, based on that lens, our physics and our mathematics and our values are dictated by that choice. Okay, so similar objects like spheres can have both an I value of 2/5 mr squared or of mr squared based on their motion and based on the relative axis of rotation. A really cool example of this is our planet Earth. If I think about Earth rotates on its own axis, giving Earth its own rotational momentum. That's pretty cool. Also, though, Earth rotates around the sun. We're an orbiting body around our sun. Therefore, the Earth acts as a semi-solid, pretty solid, and generally a sphere as it rotates about itself. But as the Earth rotates about the sun, it acts as a point mass relative to the sun. It is the exact same object that simultaneously has angular momentum similar to 2/5 mr squared about its own axis, and also has angular momentum of mr squared about its sun, about its center of orbit in its calendar orbit. Okay? Two examples. I wanted to just talk about this. Hopefully it makes sense. Hopefully it clarifies things, especially as we think about our angular momentum conservation. There have been some struggles with that, so hopefully this clears that up. If you have any more questions, you drop in the comments, you send me an email, or as always, you ask me in class. Until next time, see ya!